Welcome to the first video lecture for the second week of the MPP Math course. We're going to start with a topic that we touched on just briefly at the end of class last time, which is a little bit of formal logic and set theory. We're going to start by thinking about necessary conditions, which is a phrase that economists tend to use when they're talking about mathematical conditions that must be true. So if you have A as a necessary condition for B, it just means that in order for B to be true, A must be true. You use the left pointing arrow to indicate it. And like I said, in if-then form, if B is true, then A must be true. Just as an example, it is necessary for my car to have gas in order to start, although that's not the only thing that is required in order for my car to start. Similarly, in order for humans to be able to survive on the surface of a planet, there has to be oxygen, but that's not the only thing required. And likewise, if you're going to buy cigarettes legally, you must be 18 years of age, but being 18 years of age does not require that you will buy cigarettes. To put it into the context you're more likely to see in your Harris classes, very often professors will talk about necessary conditions when it comes to maximizing or minimizing a function. So in order for point A to maximize some function, g of x, we know that the derivative of g of x at point A is 0. However, that does not mean that it is a maximum. We need to also check the second derivative to be certain of that. In some sense, sufficient conditions can be thought of as the inverse of necessary conditions, and you'll see what that means in just a moment. So we say that statement A is a sufficient condition for statement B if knowing A is true implies that B is true. In other words, if you know A, it is sufficient to know, that is sufficient information to know that B is true. So if A is true, B absolutely must be true. Just to give you a few examples of that, for example, on a standard grading scale, if you get more than 70% correct on the exam, that is a sufficient condition to pass the exam. Similarly, if there is rain falling outside, that is a sufficient condition to conclude that the ground is wet. Notice that that is not a necessary condition because you could have a sprinkler on, you could be watering the grass. So rain falling is a sufficient condition to conclude that the ground is wet, but it is not a necessary condition to conclude that the ground is wet. In another example, if you have captured an image of a virus, that is sufficient information to know, in our world anyways, that the image was taken using a microscope of some form. And to put it in a more standard format, the kind of sufficient conditions you're likely to see, if you know that point A maximizes some function g of x, that is sufficient information to conclude that the derivative of g of x at point A is 0 and that its second derivative is negative. And we'll come back to that last one in just a moment because very often we talk about something being simultaneously necessary and sufficient. And basically what that means is that if you know A is true, B must also be true. The reverse is also the case. So if A implies B, you must know that B implies A. For example, if you know that some person, Anne, is younger than Jim, that is both necessary and sufficient to conclude that Jim is older than Anne. If you know that today is neither Saturday nor Sunday, that is both necessary and sufficient to conclude that today is a weekday. And if you know that Jack is a father, that is both necessary and sufficient to conclude jointly that Jack must be both male and a parent. That last example from last time was what we called both a necessary and sufficient condition. That is that if you know the derivative of g of x is 0 and that its second derivative is negative, that is necessary and sufficient to conclude that point A maximizes the function g of x. All right, so that's basically all we're going to talk about in terms of formal logic. It's just the kind of things you're likely to see here at Harris. We're going to move on to talk about set notation, typically, if you're defining a set, you can either just list out its items or you can describe the items. So, for example, you might use the notation that for set A, the elements of set AX are such that those elements must be odd and must be between 0 and 8. So in this case, we would conclude that the numbers that we listed above, 1, 3, 5, and 7, are the members of set A. So that same set can be described in either format. So we'll now look at some notation mathematicians use when describing sets. This curlicue means that you could replace in a sentence with is an element of. If it's hashed out, is not an element of. The sort of C bracket means that a subset, and the reverse C means superset or is contained by. So to make it a little more concrete, if we have sets T and S shown here, we know that the number 1 is an element of T, the number 4 is not an element of T. We know that T is a superset of S, and we know that S is a subset of T. Notice that superset and subset are inverse relationships. So this is a moment for you to just practice a little bit of that notation. You might pause the video to work through the example problems. And here we have the solutions just to check your work. We often need to put sets together in different ways. So a union will be when we combine all of the elements of either set. So anything that appears in either set will be in the union of the sets. An intersection is a set containing just the elements that are in both sets. And a complement is defined based on a universal set. So for example, you might be thinking about all real numbers as the universal set. You could say all positive numbers is the universal set, all integers is the universal set. To take a complement, you have to first define the universal set, and then a set's complement is every element of that universal set that is not contained in the set itself. So when you get to doing more complex unions and intersections, it's useful to know that the order doesn't matter, they're commutative, and they are associative. So again, it doesn't matter if you take one set of unions first or the other set of unions first. However, it does matter if you have a set of unions and intersections to deal with. So for example, if you're interested in taking the union of an intersection, what you can do is first take each of the unions separately, and then take the intersection of the result. If you need to take an intersection of a union, you can take first the separate intersections and then combine those with a union. So now take a moment, pause the video, and attempt these practice problems. So notice that the union of A and B is all of the elements from A and all of the elements from B. The intersection of A and C is just the set A, because the set C was all odd numbers and everything in A was odd. The intersection of A, B, and C is going to, again, because A was already odd, just be the intersection of A and B, which is the numbers 1 and 3. And finally, notice that when we take the intersection of B and C, we get the numbers 1 and 3. When we get the union of that with the intersection of A and C, that was just set A. So we get back 1, 3, 5, and 7, which is set A. And with that, we're done. Time to move on to the next lecture.